You're listening to a podcast from 702 and Cape Talk.
702 and Cape Talk.
The Naked Scientist.
And our lines are open for you. Call us now on 021-446-0567 or 1188830702. We missed the slot last week because of the Fees Must Fall March, but the Naked Scientist is with us. Good morning, Chris. Nice to chat to you again.
Good morning, Reedy.
Thank you so much. Okay, so let's start here. I have a question from Andrea. Andrea wants to know, what is the universe made of?
Well, the universe is the universe. Everything that exists is the universe. If you're a mathematician and you're familiar with the idea of sets, then when you draw that rectangle and you call it the universal set, epsilon, then that means everything. And everything inside that oblong area is the set. Well, the universe in this case is the set. Everything that exists is the universe, and before the Big Bang, when the universe popped into existence, there was no universe. Within the universe is a lot of empty space, and within that empty space are aggregations locally of matter, material. And when the universe was first formed, it was mostly all hydrogen. There was a whiff of helium and just a trace of lithium, the element number 3 in the periodic table. Beyond that, there were no other chemicals made by the Big Bang itself. Subsequent to the Big Bang, the creation of those elements and those elements getting together in the early stars, they've now been fused together to make bigger and bigger elements, and so all of the stuff that we're made of, all of the complicated chemicals that are in our bodies, the big elements, they have come from stars that have lived and died billions of years ago.
Very interesting. Thank you very much. There is another SMS here. It says, if a person were to be instantly exposed to outer space, perhaps something like an astronaut opening his or her spacesuit while floating outside their vehicle, would the person explode first due to the lack of air pressure, or freeze first because of the lack of heat? That's from Ahmed.
The first thing that would probably happen is that the individual would lose consciousness, because the one very important function a spacesuit serves is to deliver a supply of air to the person. If you don't have a supply of air, then you're not oxygenating your blood. And if you're not oxygenating your blood, you're not supplying oxygen to your brain, which has one of the highest metabolic rates in the body in terms of its demand for oxygen. In fact, your brain, while it contributes only a couple of % to your entire weight of your body, it consumes about a fifth of the oxygen that you consume or need at any one moment in time. So if you don't have a supply of air at atmospheric pressure, then you're going to deprive your brain of oxygen and you're going to lose consciousness. And this is why on an aeroplane, which isn't even in outer space, if it depressurizes, one of the first things to happen is some oxygen masks come down. Put these oxygen masks on, this will stop you losing consciousness. So the astronaut would certainly experience that. It's unlikely they would explode because they would be wearing a suit anyway, and the suit would exert inward pressure on their tissues and stop them swelling up and exploding. The other point that's alluded to about temperature is an important one, because space is a place of extremes. If you're in the path of sunlight, then the energy coming into your body from the sunlight could cook you at hundreds of degrees. But if you're in a shady place, or you're on the side of your body facing into outer space, the ambient temperature is just above 0, as in Kelvin. And for that reason, it's extremely cold. So one half of your body could be very, very cold, the other half could be very, very hot. So I think it would depend on where the astronaut was, whether or not they froze, cooked, or exploded. I think the latter, though, very unlikely.
Right, let's go to, is it Cherise in Johannesburg? Good morning.
Yes, hi, good morning. My question is, why is it that infants, particularly babies, probably babies from, birth age onwards, they blink very long? So, as adults, we need to blink very often, otherwise our eyes dry up. But as babies, I've noticed babies can keep their eyes open for a very long time before blinking.
Do you know, I have not noticed that. And I wonder if it might be that we're being a little bit sort of subjective because I haven't measured it. And we'd have to measure the blink interval. Maybe it's because when we're staring at someone's eyes unblinkingly, that's a sign of, having got more attention. We know that humans, when they're adult at least, and they attend to something, they often do reduce their blink frequency because they don't want to miss something. And this is why people who spend a lot of time working on a computer will say they get quite dry, gritty eyes, because long-term engagement with a screen can reduce the blink rate in your eye. I wonder if the babies, therefore, because they're attending to you or looking at your face when you're looking at them, and they're so interested in what they're trying to make sense of in front of them, that this engages that attention circuit, and it suppresses the blink frequency in the baby.
I've also observed that, and you think, blink, aren't your eyes getting sore? But they carry on focusing on that one item or face. Thanks, Cherise. David in Cyrildene. Good morning. Good morning.
Good morning. Could you tell me, can neutrinos exceed the speed of light?
No, everyone thought they could, David, but and that was the famous announcement last time when people sent streams of neutrinos from one place to another and concluded they were travelling there faster than the speed of light, and then they found actually it was a flaw in the way they were making the measurements. As far as we know, Einstein said there's a speed limit in the universe, and the speed of light is that speed limit, and nothing has broken it.
Okay, thank you. Liz in Sandton, hi.
Hi, I'd like to know why I sneeze when the temperature drops slightly.
Oh, hi, Liz. Well, there's a whole range of things that can trigger sneezing. One of them is exposure to bright light. This is called the photic sneeze reflex. About 1 person in 5 appears to be affected by that, and it does appear to run in families. I know I get this. If you go out on a certain, from a darker environment to a brighter one, it makes you close up your eyes, wince a bit, and it makes a tickle in your nose and makes you want to sneeze. The same can happen with other stimuli to your airways, though. The nose has got lots and lots of nerve fibres in it. Their role is to determine the temperature of the air, if there are any bugs and nasties in the air, and signal that back to your respiratory system, the nerve circuits that control how you breathe, and so you can take avoiding action and so on. It's perfectly possible that the same reflex that detects when there's a bug or an irritation or a virus in your nose and triggers a sneeze to clear it is also being stimulated by extremes or changes in temperature, perhaps in you. I would speculate that that's probably what's going on.
Somebody wants to know, why can't you tickle yourself?
Yeah, this is actually a very important and very interesting scientific phenomenon. While you can tickle yourself a bit, and everyone listening can try this, if you run your tongue across the roof of your mouth in a sort of naughty way that you might do if you were trying to kiss someone passionately, you can elicit quite an excruciating tickly sensation, but all the same, it's still not as unbearable as someone actually clasping their fingers either side of your tummy above your hips and tweaking you, or doing the same sort of crab's claw movement on the sides of your knees. We think that the reason that you can't tickle yourself is because there is a region of your brain which is at the area where the back part of the brain, the occipital cortex, and the temporal lobe and the parietal cortex all meet. And in this area of the brain there appear to be nerve cells whose job it is to look at the signals that are going out of your brain to make you do something. They compare the signals coming back in from the body, and what they're doing is saying, well, I'm making movement X and I'm expecting sensation Y to come back in, and one cancels out the other. And the reason for this is to stop you getting distracted by things that you do yourself and getting fooled into believing something that you've done is something happening to you externally. And the reason this is interesting to brain scientists is that there may be something changing in this area of the brain in people who have certain types of mental illness, which is why people suffer from things like hallucinations. There's also a researcher called Olaf Blanke who works in Switzerland, and he has managed to elicit out-of-body experiences in normal human subjects by deactivating this area of the brain. So he takes human subjects and uses a magnetic field applied to the brain to deactivate temporarily this brain area, and his subjects all experience a sensation of their own body outside their body, trying to interact or argue with what they're trying to do. So they all describe a shadow person who's a bit behind and to the side of them. And when they say, reach out to take something, they see this other hand, or they experience the sensation of another hand in parallel with their own hand, trying to also take what they're trying to take. And they can't tell that that's them, because they all say, it's trying to take the card or pick up the key. And so we think that this area of the brain is also responsible for abolishing tickle sensations, which is why you can't tickle yourself.
We've been busy tickling ourselves here in the studio, and I was waiting to hear if anyone laughs. Everyone has a straight face, so it's not working, hey? And this Nolwazi, you can stop.
It works
now.
on me.
Bear is in Bloberg Sands. Hi.
Morning, back to you. Just a question. I was on a flight to Johannesburg the other day, and the pilot mentioned that the outside temperature was -40. And I'm sure it's pretty cold for most people. Yet when I had my hand against the window, I could feel my hand getting quite hot from the sun. So if it's so cold out there, why is it not hot? I couldn't understand why. I was looking at sunshine. Okay. Yeah.
Hi, Barris. Well, the reason that the Earth's surface is nice and warm, the high atmosphere is really cold and space is really, really, really cold, is that the atmosphere is for the most part, transparent to visible light and mostly transparent to infrared. And what do I mean by transparent? In other words, when you shine light, which is the source of heat energy coming to the Earth, at the atmosphere, most of it goes straight through the atmosphere without interacting with anything. Therefore, it doesn't give any energy to the things it goes through. Therefore, those things are cold. But when it hits the Earth's surface, as we know, of course, it warms it up. Because if you put a black piece of paper on the ground on a hot day, that paper gets hot because the energy in the light hits the piece of paper, is absorbed by the material in the paper, and is converted into vibrations in the atoms and electrons, which in turn increase their temperature because they're vibrating more. That radiation is then sent back into space because long wavelength infrared rays come back off and go off into space. The reason that you felt warm in the sunlight is because you placed something in the path of the light hitting the aeroplane, your hand, which would interact with the light, absorb the energy and convert it into that same heat energy that would happen at the Earth's surface.
Dion wants to know, please ask the Naked Scientist if robots will take over the world one day. Will computers one day not need us anymore and find us to be a virus?
Well, this is the stuff that these science fiction movies are made of, isn't it? And the whole idea that we make these computer systems initially and ostensibly to help us. We write computer software that's very good at teaching itself to do things, and it subsequently decides, in inverted commas, that actually these human things are a bit of a nuisance and a bit dispensable because they consume a lot of resources, they make silly decisions and they make mistakes all over the place. And if we're looking for optimization, we probably should get rid of them. That's the whole premise of a lot of these programs. It's certainly possible to write computer code that can teach itself things, and Google acquired the rights, I think, for about 400 million to a company called DeepMind, which was created by a Cambridge student called Demis Hassabis. And that software that he wrote, one of the things it can do, because they published a paper in Nature about a year ago showing that it could do this, they set their software on an old-fashioned computer game. So they gave it access to an old computer game. It was the game Bat and Ball, where you had to move a flat bat up and down the screen and knock a ball, a blob, which goes backwards and forwards across the screen, and you had to sort of play tennis with the computer. They gave their DeepMind programming no instructions about how to play this game or how to win or anything like that. And within a few hours, it had taught itself how to play the game and how to win that game as well as any human. It could pretty much beat anybody's score. So we certainly can write software that can teach itself things. We can certainly endow machines with artificial intelligence in that way. Whether or not that means that ultimately it will arrive at the situation that the movies would have you believe exists in 2200 or whatever it is, we don't know. But I think there are a lot of bright people around. Mm-hmm. I think that they can anticipate these sorts of things. And when you drive a speedboat, you have a kill switch. I strongly suspect that they'll have some way of having some kind of kill system built into these things so that there would not be a risk of that happening.
Is it Tanda in Krugersdorp? Good morning.
Hi, I'd just like to know a little bit about melanin and its relationship with the pineal gland.
I think you're referring not to melanin, but melatonin, I think, is what you're referring to, because melanin is the brown pigment in the skin. Melatonin is a chemical which is similar to serotonin, a brain nerve transmitter chemical, and it's produced by the pineal gland, which is in the centre of your brain, part of your hypothalamus. And melatonin is your sleep hormone. When you go to sleep, you produce a surge of melatonin, and this has a sleep-inducing effect throughout your body. In fact, if you want to combat the effects of jet lag, then you can take some melatonin, and this makes you feel sleepy at the right sort of time, the right time for where you're trying to go in your journey you're making. And because it's a physiological and normal sleep trigger, it means that you sleep naturally and the normal phases of sleep happen in your brain rather than a drug-induced or gin and tonic, otherwise known as gin and tonic-induced sleep on the aeroplane, which is not necessarily a natural sleep and can actually lead to you arriving at your destination feeling less well, let's say. So melatonin, very important hormone because it induces normal sleep patterns, and it can be given exogenously in order to facilitate sleep, but it's produced by the pineal gland and in response to signals from the body clock, which knows what time it is and therefore knows what time you should be going to bed.
Shall we go to Janelle in Parktown North? Good morning.
Good morning, Rudy. What I want to ask the naked scientist, because of the pending drought, I want to purchase a water tank to harness water from the gutters. How do you work out the feasibility of the volume? I've got a thatched roof home, so I can only harness from a very, very large carport. Is it worth it? Can one drink the water? But most importantly, is it worth it to purchase a water tank in order to start harnessing water like this?
It's definitely worth storing water. The amount you spend doing this will be dictated by how much you're paying for the water that you would use, and whether or not the water is going to be very useful to you. Now, as you say, you've got a carport, and that presumably has got a reasonable roof that can collect water. You'll have to think about, well, how big is the roof area, and how much rain is likely to hit that roof. The way it works out, you've got to imagine that the rain is falling on a surface area of ground, and you can work out what the rain density is. You can look up, there will be data for your area. What is the rainfall for my area? And this will tell you what the average, the per square metre rainfall will be for your particular patch of the earth. You can then extrapolate that to your garage roof or carport roof, and this will tell you roughly how much water you can expect to collect in a year. Then you can ask yourself, well, how much water do I use and what do I want to do with that water? Now, water coming off a roof like that, most people don't drink that water because you can't guarantee that safe water, because the roof gets dirty, things land on the roof, things get deposited, let's say, on the roof, and they will get washed into your water supply. Now, some people put in place what's called a clean catch or first flush system. What that does is that it takes the first load of water that comes off the roof with all the rubbish in it, collects it separately, and then the overflow water is the clean stuff, and that goes into your tank, and then you chuck away the first flush. You just make it drain away harmlessly. That's one way of doing it. Others have ways of treating the water. Other people use that water that they collect to do things that you don't need nice drinking water to do, such as water the garden, top up fish ponds, do washing, wash hands, that kind of thing. Things that are not for human consumption, but which otherwise are a big water burden. And if you work out what you're spending on your water, and then you work out what the infrastructure is going to cost you, then you do a simple sum and you say, this is what I think it's going to cost me, this is what it's going to save me each year, therefore there will be a payback period. Am I comfortable with a 3-year, 5-year, 10-year, whatever payback period? If you are, and the lifetime of the stuff you've put in place is 20 years and the payback period is 10, then you're in business.
I have a question here, and I think it comes from our conversation yesterday. We're talking about the water crisis in South Africa, that we're running out of water, our purification and storage systems are below par, and so on. And the El Nino phenomenon was mentioned. So somebody who wants to know, as a follow-up from yesterday, I understand that the El Nino causes drought and all sorts of things, but what causes El Nino? That's basically...
Well, El Nino is the name for a patch of warm water that wanders around in the Pacific Ocean. It goes backwards and forwards across the Pacific, and it will therefore be dictated by ambient air temperatures, ocean currents, and so on. But this has the effect of influencing climate, because as air travels across the ocean surface, it picks up heat from the ocean, it picks up water from the ocean, and once you've got heat and water in the atmosphere, you've got energy in the atmosphere which can then influence where rain falls and in what sorts of volumes. And there is this sort of yo-yoing effect of El Nino going backwards and forwards across the Pacific, because either Africa has a drought or South America has a drought, depending upon what El Nino is doing. So... What's the long-term effect here? Well, if we increase the energy input to the Earth, or the energy trapping, the amount of heat close to the Earth's surface, then more energy goes into the oceans. If the oceans have got more energy, then the ocean currents are distributing more heat energy, and this means you're giving the atmosphere more heat energy, which means storms have potentially more heat energy to play with. And so that's why people are also saying, regardless of these existing patterns, climate change owing to global warming and so on, can also intensify other weather systems. And intensify doesn't just mean more floods, it can also mean more floods in some places, but fewer rain elements or episodes in other places.
Is it Chris in Braamfontein? Good morning to you, Chris.
Morning, Ricky. Thanks. I just need to know from Chris if the science can actually say how the wind came about. Was it there before the Big Bang? Is it still in the same amount, or does it somehow perish?
What, the wind?
The wind, yes.
Well, how is wind formed? Okay.
Well, where wind comes from, wind is a movement of air. Why does air move? Well, why does anything move? Well, things move because of a difference in pressure. In other words, there will be areas of higher and lower pressure around the Earth's surface, and because things flow from an area of high pressure to low pressure, that's the air moving and spreading out to occupy areas of lower pressure, and that's what we experience as wind. Why do you get pressure differences? Well, you'll get some areas where, for instance, the sun has been heating up the surface of the air, the surface of the land, and that heat is then transmitting into the overlying air, and it's making the air hotter, making it expand, making it get less dense and rise. This will leave behind a patch of lower pressure, so air will move into that patch of lower pressure from surrounding areas, and that's why you basically get wind, and why you can also get things like sea breezes.
Is it Kanyiso in Rustenburg? Good morning.
Morning. I'd like to know, why is it that if you've got two twins, one is on Earth and one you send on space, why does the one on Earth grow faster than the one on space?
It's not grow faster, it's age faster. The experiment that's been done is with two highly precise and accurate clocks. And if you synchronise them on the Earth's surface and then you put one on a fast-moving vehicle, usually they use an aeroplane, and you send that one on a couple of laps around the Earth, and you leave the other synchronised clock on the Earth's surface. When the plane comes home and you bring the two clocks back together again, you see that they are not showing the same time. The one which has been travelling at high speed on the aeroplane, time has gone more slowly, it's aged less fast than the clock which was on the Earth's surface. The reason for this is because of relativity, and as the clock which is moving at high speed is closer to the speed of light, it experiences time passing at a slightly different rate for it than the clock which is on the Earth's surface, which is why you see this disparity. So going back to your twins or your humans, the one that stays on the Earth is moving more slowly than the one that's in orbit in space, and therefore time passes a bit more slowly for the one in space compared to the one on the Earth's surface, and therefore the one on the Earth's surface has aged a little bit more by the time they come back to Earth together.
Chris, have a lovely weekend. We chat again next week.
I'm looking forward to it already. Thanks, Reedy.